Alright, so for today let's try to implement some movement for the game. So far we have, let's check, only the player moves around, but let me zoom in. But the enemies don't do any movement, so that would be interesting to see. Like the enemies also moving around, maybe following the player. And one idea is to maybe use a star to do pet finding. And yeah, basically each turn the enemy will move one step. And yeah, now we can try to think, well, do we want this to be a turn-based game, or um, you know, I guess we'll see. But yeah, the idea is I want to have the enemy also move towards the player. And I have this older project which I implemented a star in C, and yeah, I'll link the repo. I guess I'll add it in the readme so that I don't forget. But yeah, and we had a star draws the path from this corner to this corner, so it should be copy pastable, right? I think it also uses ds.h for some stuff, if I remember correctly. Yeah, it was. So hopefully it should be straightforward to implement also in this game, mainly because this is a square map. We have walls like obstacles, we have floor, so it should be, I think, I don't know, we'll see how this one goes. So we have this astar.h file. So we had the position array, which I guess we already have some stuff like array and all of that. So probably we just need, I don't know what these are. We just need pet find, the function. Oh, so it takes in obstacles, width, height, the start, the end, and then it gives you the position array output. So it gives you an array of steps. So I think yeah, it should be straight. Like if you think about it, let's refresh this page. Oh, let's restart the game, I guess. So we can basically just draw the map in here, right? So the map looks something like this. Not exactly, but it's something, I mean something like this, right? So yeah, you can think of it like this. And yeah, I mean I cannot set waypoints, but you can imagine. So I think it should work to just steal stuff from my old code, and yeah, I think that's a good idea. So let's go straight into main.c, and yeah, I think we just need to implement the pet find function, and then we'll figure out a way to get the obstacles like this. Yeah, why not. So let's go into C. Let's take this and let's see where, oh my god, oh my god, I mean it's pretty huge, but yeah, well, I guess it's pretty funny because world had a map like this, so it might be even easier because we already have something like this in the world structure, whatever it is. Somehow, I mean, we have the array, right? This array and the width and height. So we already have the structure, let's say. Okay, so yeah, let's just see what we can do here. Damn, it was quite a lot of stuff. So I mean, yeah, let's just try to go step by step through the a star function and try to get it to work. So where can I? Okay, let's do it here. So basically, a star should take in the world, right? So like the information. Okay, let's not like the information of the obstacles and everything, right? The position of the player and so on. Then it should take a position which I think we called uvec2 and a position for the end. So where do we start and where do we want to go? And then it will give us an array of points. So here I would actually just use this dynamic array, and sure, let's call it p. So p is gonna be the points that form the path, let's say. So the path, yeah, why not? Okay, we had this result. Okay, so this one was returning errors and stuff, so sure, why not? Result. Then we have number of nodes. I mean, I guess maybe makes sense. Funny, we don't even need to modify anything, it just works. It could be unsigned. Okay, and the first step of I guess a star, how it's working, we have an open set which uses a priority queue. Already have the priority queue in ds.h, so that's fine, even though we are using C and it sucks. And in this priority queue we keep all the nodes that we can visit. So I think on Wikipedia it was using this expanding name, so the nodes that you can expand or visit basically. And then we also have, I think, like the parent relationship of the nodes. This one, I think it was just a list, so not that interesting. And I don't remember, but I mean, I remember that we also had something like visit, but yeah, no, doesn't matter. So let's just take this stuff. So these are the nodes that we want to visit. Only the start node is known. Min heap, yeah, whatever. I mean, we have the priority queue. Okay, and the priority queue init wants a function to compare items, right? So that's how so it takes in pq, the priority queue, a compare function, and item size. Interesting. I guess I was using like, yeah, the ds.h used in this project is older, so it's a bit different, but shouldn't really matter that much. So position compare minimum, this was the function that we need. So yeah, I mean, pretty straightforward, I would say. We just have to position node. Okay, yeah, so we also need this thing. Yeah, let's include it. So this is specific to a star. I guess we'll call it node. It doesn't really matter, to be honest. So we have a uvec2 for the position, and this f, which is the cost, but it's the total cost. Let's say it's the, or was it? I mean, I guess we'll see, but because we have the g-score, which is the cost from the start to the current node, and f-score, which is the g-score plus the heuristic. So it's yeah, f is the total score, let's say, of one node. Yeah, anyway, I mean, we can just say a star node or something. So if we want to compare this thing, we can just convert them to a star nodes like this. Maybe we can even type defit to write less stuff. Okay, like that. And now this one also takes in the size of an item, and I mean, obviously we keep a star nodes in this priority queue. So yeah, okay. Yeah, and we order these nodes in the priority queue by their score. So we want the node that has the minimum heuristic plus the cost from the beginning to be the smallest. So it's like the best option for our enemy to choose from, right? Okay, then we have the start node, which is basically the beginning, right? So the start node, let's just say a start node. Well, here we can do something like, oh, you know what, if I remember correctly, ds.h, I might be wrong. I think I have in ds.h an example of a star. Yeah, I do. Oh, that's interesting. Maybe this example is better, actually. Yeah, because it uses the new version. Okay, perfect. Okay, so it's better to use this one, right? Anyway, so we have the start node, which is a star node, and yeah, if you think about it, right, the beginning, the first node, the distance from the beginning to itself is 0, and the heuristic, here I used Manhattan distance. I mean, you can use any heuristic you want. Manhattan distance is just the difference in x plus the difference in y for the points. So we do the difference between start and end. That's pretty much it. And I guess Manhattan distance, we can just copy paste it as well. And we can use uvec2, uvec2, and here the abs. Oh, I mean, I guess we should convert these things to int to be able to do the thing, right? Because yeah, we want to subtract from the larger one, but it's easier to just do that. Okay, so we have the start node, we have to add it, right? We have to add that into the priority queue, and we have a function for that. Pretty easy, don't even need to think about it. And then we have this came from, which I already explained, but yeah, basically came from. So we have node n, let's imagine, I don't know, like a random node on the path. If we use came from as a hash map and we pass n into it, we get the previous node or the parent node, if you want to think about it that way. So that's the purpose of came from. Yeah, pretty weird, pretty wild name. I think that's how it was called on Wikipedia. Maybe I just kept the conventions the same. But yeah, initially we just initialize came from with -1s. So we don't know any relationship between any nodes on the map. We just have it as -1. And then G-score again. This one is the cost from the beginning to the current node. So the only score that we know about is the first one, which is 0, but for the other ones we have no idea because we haven't touched them yet. So let's just add also this one. Int max. I think int max came from somewhere, but I'm not sure. C limits. I mean, I don't think it was. It's limits.h. Okay. Limits.h. Yeah, and you might see this one, position hash, which is what is that? And yeah, position hash basically, like, I was too lazy to implement a hash map for UVec, so I just said, okay, let's just create a hash function and use an array as a hash map. I mean, it's still a hash map in a way, but it's the poor man's hash map, let's just say. So how does this one work? Well, we have a UVec too, and we just convert from a 2D array into a one-dimensional array index, right? So we get the y, multiply it with width, and add x. So that's how we get the 1D index, right? For our start point. So, makes sense? Makes complete sense. Then we have the same thing for f function, and I guess f score. And the f score is, as I said before, the g score plus the heuristic. So again, we don't know anything about the other nodes. We only know about the first one, and since the g score is 0, we only have h, and again, h is just Manhattan distance. Just keep that in mind. Okay, then we need like an iterator. I just created this one as an A star node, and then we have a while loop until we empty out the priority queue. Okay, so we want to go through all possible options and build the thing. Okay, so first step is to get the first one. So here it's, I think I had a comment that getting this thing is all log n. Yeah, I think it's a log n because priority queue is some kind of a tree, but in my implementation the priority queue is an array, but you move through it using an approach similar to binary search. So that's the idea there. Like you go in the middle, then left, right. So it's like a tree. That's why it's log n, because you split halves each time. So it's gonna be log n. Anyway, so yeah, here we get the current node and we get the index of that node. P was the position and F is the score, right? So yeah, so yeah, we get the current index, which I have no idea why I needed that, but anyway, I guess for G score and F score, yeah. Anyway, I also wanted the position. I mean, let's just go through these. Oh, yeah, just to check that the position is equal. So position equals reconstruct path. Okay, let's see position. Okay, I mean, I can close these ones. Position equal. I guess position equals is a pretty obvious function. We just check if x and y's are equal. Then we have reconstruct path, which is more interesting in my opinion. Well, I guess not that much. I mean, reconstruct path, if you got the idea of what came from does, it should be pretty obvious. We just take the last node, and then if we call came from on that one, we get the parent, and then we keep going like that in a while loop until we get to the beginning. So that's the idea of that. So here we have a ds dynamic array p. Let's see, ds dynamic array append, and here we want p and the address of current. Yeah, then we get the current index, which is like for the hash map, the imaginary hash map, let's just say. Okay, and then we have uvec2, again another one, and we need to append it as well. Yeah, I'm just hoping that we don't have any memory errors, hopefully. And I think return defer is ds return. We don't have any defer. Yeah, so for return defer we needed this stuff. So I think a star was returning a 1 if it was working. Hopefully that's the case. Okay, num directions. Wait, where does this one come from? I guess it's some define. Yeah, I mean, I don't know why it was there, but anyway, let's just have it here. So uvec2, right? So we have the up, down, left, right directions as an array, and the number of them. Yeah. So I think I saw this trick in a coding video or something like that. Having size of the array divided by size of the first element, and you get the number of elements. Pretty neat. Okay, so we have the 4. Right. We get the neighbor, uvec2. Right, like makes sense. We get a neighbor index. Right. We have the current index, and the neighbor. So we can make some things on it. Okay, like sure. if you go out of bounds, this one is interesting. Oh, yeah, so if you go below 0, above width, and so on, and then we have the check for walls, right? The check for walls, and maybe it was easier in the other one because yeah, here we have a dynamic array. So let's try to get that. So tile kind, I guess tile, and then this dynamic array get world tiles, and we use neighbor index, and the address should be tile, I think. Oh, and this one also wants, I mean, yeah, just because I liked pointers, I did it like that anyway. So here it's gonna be interesting. Do we want tile to be different than wall ch, or maybe do we want another rule? But yeah, I think that's fine. Like not being able to walk on top of walls should be enough. Okay, so here we had this d is the weight of the edge from current neighbor to whatever. Yeah, so we had this g score, right, which is basically g score plus 1 because we make one step, right? So this is the new g score, let's say. And I mean, yeah, because it's a grid map, we like the cost between two adjacent cell is gonna be 1. It's not gonna be like in more complicated problems where maybe you compute a distance, like I said here with d, but in this case the distance is 1 because we have a grid. So if this new score is better than the old one, which I mean we don't know for sure because yeah, it's like current point plus 1, and here we have the old g score of the neighbor. So if we have a better path through the new path, I guess, we just have to update it. So this path is better than the previous one, I mean obviously. So yeah, we just want to update the parent. So the parent of neighbor becomes current index, right? So the path through our current node is better than the previous one, so we just update that. Then we update the g score to be the better one, and f score just becomes g score, like the new one, plus the Manhattan distance between neighbor and end. And I mean, if you think about it, f score can become worse in a weird way, but yeah, that's the idea of a star. Like we found a better way so far through G, but yeah, the Manhattan distance can become worse, I guess. I don't know if it's possible though, but if you think about it, maybe. Okay, so now we need to, I guess, go through the open set, see if we find a node. Like if we find the node again, like, yeah. Then let's just think about it for a second. So because yeah, we go through the open set, and if we find the neighbor, then it means that we found it. And then if we don't find it, then we have to add it. But Yeah, it was pretty weird. I thought we had to update something on it, but maybe we didn't. Yeah, anyway. Yeah, I thought we had to update something on the node, but yeah, maybe we don't need to. Maybe it's just that if we found a better path, we need to. But I don't know why I used ref. That's why I thought we had to update something. Because I think this should also work. Like you don't need to use all of that. Yeah, anyway. Yeah, and I mean, I'll just try it like this because I think it shouldn't need ref. Yeah, sure. And then if we don't find it, then we have to add it in the priority queue. And if we don't find it, then a star node yeah, basically we have to add it in the priority queue. Maybe like we add it on top of some or something. So yeah, we'll see about the freeze. We don't really care about it. So yeah, if I look at this thing, it's pretty interesting. So yeah, let's try to run a star from the enemy to the player or something and see the path. Right, so I guess first of all let's just put here a comment for what the type of this thing is. So I think it's UVEC2s, right? UVEC2, because it's important to remember that. So let's do it here, like why not, after parsing. We can even just comment all of this thing out, and then let's make a dynamic array p, dynamic array init, and then we do address of p, size of UVEC2, and then a star. And yeah, here we need the address of world, start, end, and then address of p. Yeah, now it's interesting for start and end. So let's do UVEC2. Well, world, I think it should contain the entity player. So let's say the end, at least the end, is gonna be world dot player. Wait, what? It's because of this. Player dot position. So this one should be a UVEC. And the start, let's just say UVEC2 start. And let's go through the world and choose the first one. So dynamic get. So world dot enemies. I think we need reference. Let's say is the first one, and we need an entity. So that's how we enemy position. Okay, let's just run it. I mean, if you don't get a segmentation fault, it's interesting. Too much for I mean, I wouldn't be surprised if it works first try because we copy pasted most of it from an older implementation, but I still expect some errors, like, to be honest. Okay, so uvec2 point ds dynamic array get. We have the p, we have the I, and we have the point. Perfect. So let's just print f something like d a new line and point.x, point.y. Let's see. This one is gonna be interesting. Okay, what? Zero, so it didn't find a path. That, that sucks. I mean, let's just see the current. Let's just see the progress of this thing. I'm curious. 18 and 3. So I think that's the first one. Huh. Fuck. Although it's a bit weird. I mean, yeah, it's 18 and 3. Yeah. So at least the first position is fine. Okay, fair enough. But then we take the neighbor, right? So the neighbor, I mean, come on, printf debugging is the best. So yeah, the neighbors look good. That's interesting. Let's see if we get into this. Yikes! Oh, so I made an oopsie doopsie. So neighbor is less than 0. It's not. Greater than width, probably not. Less than 0, greater or equal than height, or or equal to wall. Okay, yeah. So if it's equal to wall, obviously. Yo, we printed something. Yo, 4-3 is actually the position of the player, right? Yeah, it actually works. What the hell? Damn, dude. I mean, it's good that we had an error because that means that we fixed it and now it works. So it's always a bad omen if you don't get an error, but yeah, that's pretty nice. Obviously memory allocation needs to be addressed, so here these freeze, we need to call them because yeah, it's well, wait, I mean, why not? I'm scared to run Valgrind on this thing, but yeah. Anyway, so let's see. Let's try to actually run a star. Somehow in the update loop. So how can we do that? Do I have a DS dynamic array? Not really. I have so many functions, but none of them are useful. Yeah, so here it's gonna be like an I. We are gonna go through all the enemies. So we need a for loop. Let's do that. So for unsigned int I is equal to 0, I is less than world enemies dot count I plus plus. All right, we'll need something like this. Then at the end, like I saw that the path is gonna be in reverse. And the last item is actually the ending, so yeah, it's not that big of a problem, honestly, because we can do something like unsigned int next is gonna be probably this is like the next step, right? So it's gonna be p.count minus 1, p.count minus should maybe be minus 2, and then we can maybe have a uvec, so uvec to step or something, and let's just take it dynamic array get from p we want next into step, and then we can maybe say oh yeah, for this one maybe we can use get with reference generally get ref, so we want a void pointer, right? So because we want to change the position. Oh, what's even cool is that here we can pass enemy position like this, right? So this should step the enemy once. Let's see if it's gonna be in a different position than usual. Yo, it is. Okay, that's cool. Let's do it. Let's do it in the update. The issue with doing it in the update is that it's gonna be really fast, I think. So we'll see how we can make it slower. Yo, it's following me. But now it's being cooked. Okay. Let's see, it's oh no. I cannot escape. Yeah. Nice. So yeah, it's actually following us. I mean, obviously it's gonna be a bit broken when it reaches our position, but that's it's part of the plans for now. Yeah, I mean, again, maybe we want it to act only when we press on a key, so it's gonna be turn-based. Maybe that's better for this kind of game to make it turn-based. But yeah, we'll have to see. I mean, turn-based seems promising. Maybe we can just get rid of the multi-threading, but yeah, I don't know about that. Maybe we can just simulate turn-based movement. So for example, we can have another thing here for input, which is like end turn, which is gonna happen only on certain key presses. So I don't know. Uh, yeah, or just like here. I guess let me do something like if input dot last key is not equal to 0, so if the key was pressed, we move the enemy. But here in this case we might want to see, let's say, which key was pressed, because if we have an inventory and you swap your items, you shouldn't end your turn yet. Like the turn should be ended once you make a WSD move, right? So that's how I imagine it. It's a bit, oh, and we died. Yeah, so I think that's pretty cool. Some stuff that I want to do, and I mean I won't do them on video because they're boring, is taking care of the memory leaks, because probably we have some, and refactoring the code a bit, because yeah, we just need to take care of this error, like when A star doesn't give us anything because the enemy is on top of us. Maybe we don't want to do this, so that's one thing. And yeah, maybe think about some items, some crafting and stuff, because yeah, we need to make the player be able to fight with the enemy. And maybe also add some kind of range, like if the enemy is too far away, they won't follow you, and like they'll have a vision range, and if you go out of it, maybe they forget about you and stop following. So yeah, that's that could be interesting to try and do in the next parts. So yeah, thank you for watching, and I'll see you next time.